Now, if you have anybody in your life who wants to get swole, I have 4 teenage sons. They're interested in sports. So we have this stuff in our house called protein powder. Muscle is meat. Meat is protein. You need amino acids to build more muscles because muscles are made out of protein. And this one contains the codes for making proteins. It carries information. Have you heard of it?
Redeem Academy.
Hey, what is up, Science Squirrels? Johnny here with Redeem Academy. I'm here to help you get the most out of your education while giving God the glory he deserves. This is it. Last lesson on cells, lesson 8. This lesson's all about the things that make up cells. I call them biomolecules. All right, I'm gonna be telling you about 3 things today. I'm gonna tell you what the 4 biomolecules are. Spoiler alert, here they come. Proteins, carbs, lipids, and nucleic acids. That's the only time I'm gonna say it. I hope you wrote that down. JK, lol. Thing 2 is, I'm gonna give you a common example of each one. And thing 3,
don't forget 3.
I'm gonna tell you the little piece that each one is made of. All right, and big question today, why did God choose to design all cells using the same 4 biomolecules? That's really why I have the biomolecules at the end of the cells unit. I really want to kind of review the cells unit by looking at what all cells are made of. If you need a notebook to follow along today, go to redeemacademy.org and you can get one. All right, let's jump in. Let me explain how these biomolecules work. Okay, well, the first thing you need to know is that all of the biomolecules minus 1 are actually called polymers. And a good metaphor for a polymer is a chain. And polymers are made of monomers. And a monomer is just one link in a chain. So words help a little bit, but let's watch a video of chain getting made, and that's going to help you understand a little bit better. So chain is actually made from wire. So here's a bunch of wire unspooling and getting pulled into a machine. And as it gets pulled into the machine, it goes through a die, and that straightens the wire and hardens the wire. And now it's getting pulled in and cut, because link by link, the chain is going to get cut and formed into individual links that make up the chain. Okay, now here are those pieces, and they're getting completely cut right before they get shoved into this other part. And then all these amazing little pieces bend the metal with extreme amounts of force. I mean, I couldn't bend a piece of 1/4-inch metal or whatever that is right there, but mechanical engineers build these machines with just the right parts so they can bend the chain. But the one thing that's left, and I'll pause it here so you can see this, right there, there's still a little gap right there where the link has been bent back on itself, but it's not going to be nearly as strong as if you weld that shut. And if you can weld that shut on every link, the chain as a whole is going to be a heck of a lot stronger. And so the next step in the process, we see this portion of the thing. Yeah, and so still those links have not been welded shut yet. This is just another view in real time. I think it said like 50 links a minute get made by this machine when I was listening to this whole video earlier. Okay, now we can see this spot right here is where it actually gets welded shut. And I was listening to the video. It has this really annoying music in the background. I didn't want to really play it, but you can see it's running a current of electricity through it. And by doing that, it's able to melt the 2 sides of the link together. And so you form a complete bond between the 2 sides, and you get a piece of chain that's going to be way stronger. So assuming we were looking at 1/4-inch steel that was being used to make that chain there, what is the strength until failure of a chain made of 1/4-inch steel? Okay, so, hey, it depends on what kind of steel. There's different values or grades of steel, but it's going to break somewhere at 3,900 pounds being lifted, 7,800 pounds, 9,500 pounds. That's really strong. That's a ton of weight on just a little piece of chain. Like 1/4-inch is not a big piece of chain. All right, so here I am at Lowe's.com, not a sponsor yet, and they're selling 1/4-inch welded chain, you know, for your playground, for your swing set, and it costs $4 a foot. Okay, and so the concept here is that's a link, the whole thing is a chain, okay? So that's the big idea I'm trying to get across to you. 3 out of the 4 biomolecules we're talking about today that make up cells are just the same little thing, like a link, that just repeats itself over and over again, like a chain is just made of the same thing over and over and over again. That's how 3 out of the 4 things that we're going to talk about today work. The small version, the link, is called the monomer, and the big thing is called the polymer. So our first one is called a protein. So the polymer is called a protein. You've heard me say that word a number of times. And the little thing that makes it up, you probably haven't heard me say this word, is called an amino acid. Okay, so you can see in there how the protein is just a chain of those little amino acids. Now, if you have anybody in your life who wants to get swole, I have 4 teenage sons. They're interested in sports. So we have this stuff in our house called protein powder. And if you look at the side of it, it has BCAAs. Those are branched chain amino acids. Okay, and if you read the back of this thing, it's going to talk about branched chain amino acids, leucine, isoleucine, valine. There's certain amino acids, those 3 words I just said are amino acids. There's certain amino acids that really promote muscle growth so that you can get stronger and run faster and jump farther and that sort of stuff. And so if you ever watch influencers who are into bodybuilding or into athletics, these are going to be words they talk about.
Oh! Somebody! Oh! He needs some milk!
But also, proteins, you can think of them as like paper airplanes. Proteins will start out as a long chain and they will fold up into shapes that make up all the things inside of cells. The reason I'm talking about the 4 macromolecules today at the end of the cells unit is because everything that is in a cell, most everything, there are some exceptions, is either going to be made out of proteins or one of the other 3 biomolecules that I'm talking about. So here's a protein. This protein is called hemoglobin, and this is a protein that's just the only thing in red blood cells that you were learning all about red blood cells. This is the thing in red blood cells. This is a little bit more of what it looks like if we don't, remember you could see like space filling model or ball and stick model. This would be more like ball and stick model. This would be more like space filling model of hemoglobin. Here's my cartoon version of hemoglobin. He looks a little friendlier. He's got 4 iron atoms inside of him, and those are for grabbing on to oxygen. And all those ribbons are actually the protein himself, and his arms and legs and face, they don't actually exist. This is just the friendly cartoon version. Now someday, when I've really made it as a YouTuber, I'm gonna buy a hemoglobin model for behind my desk. Okay, here's the $69 extra small 4 centimeter version, but I'm gonna go big someday, extra large 12 centimeter. That's gonna be like, what, 12 centimeters, like this big. Okay, yeah, and it shows like the hemes. This is really not worth the money. I don't know why anyone would ever buy this. Oh yeah, here we go. This website has a 3D model of hemoglobin that you can like manipulate and move around. So each like yellow thing represents like 1 amino acid that I'm clicking through, okay? And then you can like move it around. It has a green subunit called the alpha subunit and the orange subunit called the beta subunit. And then those iron atoms that you saw in my little model, they're right here. They're in this other thing called a heme. And that right there, let's see if I can zoom in on that. That is the heme. Oh yeah, that's it. That's the heme. Oh man, I'm in the heme. And that's the iron right there that my cursor's pointing at. And so when you breathe, your iron atoms like oxygen and they grab on. And you literally have in every red blood cell, you have 1 million hemoglobin molecules in every red blood cell. And then you have, I looked this up the other day, you have trillions, no, you have, I think it was 37 trillion red blood cells in your body, and then every one of those has 1 million hemoglobin molecules, and every one of those will absorb 4 oxygen atoms when your blood comes to your lungs, and then it'll go to your muscles and dump all that oxygen. It's like, what an amazing design. I mean, this is how amazing God designed the molecule of hemoglobin. So when hemoglobin comes to your lungs, it will change shape to receive oxygen because the pH is, I can't remember if it's acidic or basic in your lungs. It's basic. And then when it goes to your muscles, because your muscles are making lactic acid, the pH becomes acidic in your muscles, so then hemoglobin's shape will change a little bit when it gets to your muscles, so then it will want to give up the oxygen. So hemoglobin is literally designed by God to absorb oxygen in your lungs and then give up oxygen in your muscles. Brilliant design. Amazing. So that's why I want a little hemoglobin molecule for my shelf, but I'm not going to pay all that money for that. Maybe I can just make one out of pipe cleaners or something. So anyway, proteins, we always see them as drawn as like these things with little ribbons, okay? Or little globs. So this is more of a globular, okay? Or the ribbon version of proteins. Okay, just going back to our cells unit, okay? You got to see aquaporin. Aquaporin's a protein in the cell membrane. In photosynthesis, you got to see photosystems. Photosystems and ATP synthase are proteins in the cell membrane. This is a great image of ATP synthase in operation. If we zoom in, we see all those little marbles that make up ATP synthase. Each one of those represents one amino acid that makes up the protein that is ATP synthase. Oh, remember this terrible thing? All the bumps on everything in there represent amino acids. Again, muscle is meat. Meat is protein. Your muscles are made out of protein. They're made out of amino acids. You need amino acids to build more muscles because muscles are made out of protein. So what are you in terms of mass? If you take all the water out of a person's body, the number one thing that you're made of protein. Okay? And so the monomers of protein are called amino acids. And the chain of amino acids put together is called a protein. And the main thing proteins do is they are parts. They make up the parts of your body. Everything in a cell that isn't made of fat is primarily made of protein. Now that brings us to number 2. This is a carbohydrate. Okay, and carbohydrates are made out of sugars. This particular carbohydrate is called glycogen. And the main purpose of sugar or carbs is energy. Okay, so you already heard a lot about this during the mitochondria lesson, the ATP lesson, that we eat sugars so that we can use the energy in sugar to make ATP to power our cells. So I'm not going to spend a lot of time on this one because I think I've already taught sugar to you pretty well. Sugar can be drawn a couple of ways. Okay, so this is the ball and stick version of a sugar molecule. And you can see the red oxygen atoms, the white hydrogen atoms, and the gray carbon atoms. Or sugar can be drawn more just as a hexagon, and that's what you're seeing in the other picture there. And so when we draw it like this, what we're showing as a hexagon is we're just showing it's a 6-carbon molecule, okay? And when we draw glycogen like this, what we're saying is there's a chain of 6-carbon molecules branching off. And so glycogen is how we store glucose. So if you, like me sometimes, go a little crazy and eat 6 pieces of pizza, your blood sugar is not going to hold all that sugar from all that pizza that you just ate. So this is how your body stores all those carbs you ate in all that pizza, all that bready pizza. And you have a little protein in, you have lots of these little proteins in your muscle and your livers, and then all those sugar molecules start branching and branching and branching. They're all glucoses just in these long chains, and it's called glycogen. And you store lots and lots of these glycogen molecules. You can store like 2,000 calories. If you're a marathoner, you can probably store 3,000 or 4,000 calories of sugar in your muscles and your liver like this. Now, because it's for running, I like to run. And so because it's for running, I drew my own little glycogen character. Here he is, tearing it up, burning sugar, out for a run. His name's glycogen. There are other forms of carbohydrates besides glycogen. Glycogen's just the human one. There's cellulose, there's starch, there's all kinds. All right, so the monomer of carbohydrates, sugars, doesn't just have to be glucose either. A chain of sugar molecules is called a carbohydrate. There's lots of different ways carbohydrates are stored, not just glycogen. But the one that animals store in their liver and muscles for later use is called glycogen. All right, that brings us to our next biomolecule that makes up cells as well. And this one contains the codes for making proteins. It carries information. Have you heard of it? This colorful guy likes to twist up in a ladder. You've heard of him. He's DNA. His less known little brother is called RNA, and the NA is the general term for both of them, nucleic acid. And their monomer looks a lot like ATP. It's ATP minus 2 phosphates, and with a slightly different base right here. It's called a nucleotide. Now, the main purpose for these guys is to store information. All right, so you have seen all kinds of pictures of DNA. They're all terrible. telling you, like all the TV shows, all the movies, like this picture right here, it's just terrible. Like, what is this? This is not what DNA looks like. I mean, it's kind of the right shape, but it's not at all the right, like, chemically accurate structure of DNA. Now, I think on this one, they're trying to go for like, oh, it's DNA's blueprints. Let's make it look like blueprints. Okay, cool. Okay, this one, it's like, I don't know what we're doing here. It's just artistic. Okay, it kind of looks like the Hungry Caterpillar version of DNA to me. Okay, this one's like, what are we, the DNA of aliens or something? This is just terribly wrong. Here is an accurate picture of DNA, and I think DNA is cool when you show what it really looks like, because it's actually made out of atoms that have chemical bonds. Okay, so this is a good picture of DNA. I'm not going to spend all the time going into it though. My picture that I've made is, for my notes, is fairly accurate chemically, but this is like exactly chemically accurate. Like you can actually see the flat bases in between and stuff. And DNA even has what's called a major groove and a minor groove. So you can see this right here is called the minor groove. This is called the major groove. So there's all kinds of fascinating things about DNA. DNA, every major groove and minor groove is 10.5 bases. So if we were to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.5, then we would have repeated one time major groove, minor groove. So there's a lot of very nerdy cool stuff about DNA. And there's different shapes to DNA depending on what temperature and I want to say what pH and saltiness there is in the solution around it. So obviously DNA is normally at 98.6 degrees for us, and other creatures, different temperatures. So anyway, here's my cartoon DNA for my YouTube thumbnail, and he's got some blueprints he's reading because he is about information. Now, as you can see, the monomer for DNA is a single nucleotide, and those combine to form a chain again. And there's another thing like DNA called RNA that's a single side of DNA, and you'll learn a lot more about this later. So the nucleic acids, different kinds of what I would call DNA. The monomers are called nucleotides, and a single strand of it is called RNA, and a double strand of it is called DNA. All right, now this brings us to the one biomolecule that makes up cells that doesn't have monomers and polymers. And this bad boy, you've already heard his name, almost, or more of it than you needed. He's just called lipids. And I wrote the word monomer polymer just so we could put a circle around it and cross it off. He doesn't do the monomer polymer thing. In fact, let's do it in red. No, do not enter. Lipids do not do monomer polymer. Lipids are categorized not by the fact that they all have a monomer polymer thing. Lipids are categorized by the fact that they are all non-polar molecules. So basically there's a bunch of non-polar molecules that are, you know, interesting molecules inside of cells. They all get into one category. It's kind of like when you're in high school and all the guys who do sports together, they're the jocks. Same thing, there's all the non-polar molecules, they're the lipids. So, what is included with the lipids? The big three are fats. So see, here's a big, beautiful cut of meat, and you see all that white stuff in there? That is fat. So we have some protein in there, but then we have the white stuff, that's fat, okay? And then we have oil, and then we have wax. You know, like when you need to wax your upper lip. I find it's always necessary to get distracted by something kind of random. Today's distraction, oil. So I was thinking about oil, I was like, what can I say about oil? And then I was like, oil, olive oil, olive oil. And then I realized I have been to a place where I watched people make olive oil. I have been to the place where Jesus was around olive trees. I must share this with you, okay? I didn't know how olive oil got made. So I have some nerding. I want to do some nerding.
Let me do this, please.
So this tree is in a garden on the Mount of Olives. Now you might, if you are a Bible nerd, you might remember that the Mount of Olives is the place where Jesus went the night that he was betrayed by Judas. Well, it turns out the Mount of Olives still very much exists. It's right across from the temple. Google Earth. Okay, here I am. I'm in Oregon. We're going to spin the globe. And there's Africa. We got to go up. Here is the Mediterranean Sea, and we're going to zoom into Israel. Whoa, I love Google Earth. Okay, there's Jerusalem. Zooming in. See if we can find the Temple Mount. Boom. It's so easy to find. So there's the Temple Mount right there. So much to say about this place if you don't know. But right across the street, right here, is the Mount of Olives. It's like a little valley. So on the one side, you have the Temple Mount, and then it goes down, and then it comes back up, and the Mount of Olives is up here. Okay, and so you can see, you probably can't see this, but right here it says Gethsemane. So there's this church that's been built right here, and there's like a rock inside this church. And the Catholics are like, this is it, man. This is the rock Jesus wept and bled on. And it's like, sometimes the Catholics get a little too much on the items. But these trees right here, there's this little garden right here. And they're like, this is it, man. This is the Garden of Gethsemane. And probably not, but there's olive trees all over this hillside still, and they've dated these olive trees, and they're like thousands of years old, maybe not quite as old as the time of Jesus. Olive trees will send out shoots, and so the organism itself of the olive trees has been there since the time of Jesus. And so it's just cool that like, oh, the Bible's actually like from that time period and is naming things about that place that are accurate. And so these trees right here, and this little garden is like a place. I think we wandered off and like we went over here and we did worship afterward when we were there. It's just cool to be in the place like this is about the right spot. And like this church right here is built like in the 4th century. Not this church, but like this church is built over what was once a church that was built in the 4th century. Anyway, these olive trees grow right here. And I've been to this place. So cool. So this is the spot right here where these olive trees that are like over 1,000 years old are growing. And olives grow on these trees. And so this is how they made olive oil back in the day. So I'm just turning this down a little bit. So, and then we saw this kind of system that they used when we were there. And so that big stone that the mule is being used to push around is called a millstone. And so they're milling olive oil. I don't know if that's the right way to say it, but they put a bunch of olives in there because olives just grow on trees and they fall off the trees and it's all mushy and gross. And so they would literally crush the olives, and there's a big hard seed in the olive, and then they put them in these weird little vat things, and who knows, they were probably making things like that out of the branches and stuff. And then this is like the exact kind of thing that we saw, and they stick all these things under a big log, and I don't remember exactly the system they used to push down the log, but then they push down the log, and then all of this oil, and there's this beautiful metaphor about how Jesus was crushed in Gethsemane, and like Gethsemane literally means like olive crushing or something like that. And so you can see the olive oil getting squeezed out of the smashed olives. And that's like what happened to Jesus as he sweat blood as he was being crushed in Gethsemane for us. And then they use the olive oil they burn it to make light. And Jesus is the light of the world. Like, whoa, man, that's so deep and cool. Oil comes from olives. And there's also, I just thought it was so profound when I was in Israel. This giant stone that's being rolled around in this big trough thing is called a millstone. And Jesus said, if you cause one of these little people to sin, when children came to him, he says, if you cause one of these little people to sin, it'd be better for you to have a millstone tied around your neck and cast into the sea than for you to do that to a person. So like, whoa, man, Jesus loves kids. He cares about how we lead children, you know? And like now I understand what a millstone is. It's a giant rock. So anyway, just cool stuff about oil, but oil comes from plants. And you can crush olives, and olives just grow like crazy in Israel. And this is why the Bible talks about olives and the olive branch and all the things that show up in the Bible. And olive oil is just a natural oil, and it's a lipid. It's a non-polar thing. and I love Jesus. You've learned about phospholipids, you've learned about steroids or cholesterol, and lipids in general. You learned about them in the cell membrane. Their main purpose is structure. And so, the class of molecules that includes fats, oils, and waxes, and also steroids like cholesterol, they are grouped together by the fact that they are nonpolar and hydrophobic. Those are called the lipids. And they don't follow the monomer-polymer pattern. So I wanted to get a chance to kind of summarize the cells unit for you and just show you how everything that cells are made of, they themselves are just made out of atoms, and they're molecules, and cells are made out of molecules, and then we are made out of cells. And so there's a simple design process God used to make us. Coming back to the big question, why did God choose to design all cells using the same 4 biomolecules? I can think of a few reasons. One, it keeps the chemistry of the world clean. Everything can be recycled and reused. 2, it shows that all living things were made by the same creator. And I'd say 3, because it's a really good system. If you got something that works really well, you don't need to deviate from it too much. So, God is good. The things He made work really good. They recycle really well within the system, and they stay connected to each other, and they all speak clearly. He is the creator. I hope studying cells has been fun for you. I've never been able to teach cells to Christians before, and one of the things that I'm really enjoying about it is it lets me say what I really think. It lets me say, man, I know I've always loved cells, and I've always had students kind of be like, God, the reason I love cells is because I see God in it. I see an intelligent designer in it. And being a public school teacher, I'm always kind of like praying for my toes because I'm crossing the line a little bit. But for the first time, I'm able to just blast it out there. God is a brilliant designer, and his design is all over creation, and we see it everywhere. So it's been really satisfying for me to be able to share all that I see in His creation. I hope you're enjoying it too. I'm looking forward to my next unit. Hope I see you there. Have a great day.